Hello, ladies and gentlemen. Let's look at question 13. Now, question 13 is about rocket propulsion, but in a different way. They don't actually ask us to calculate the rocket force of the thrust. Rather, they give us a graph. Okay, so let's take a look at the situation first. Here's a model rocket. The mass initially is 1.3 kg. Then after that, it burns fuel. The fuel used is 0.23 kilograms per second. And then after that, it flies up into the air, and when it flies up into the air, the final mass of the rocket after some time is 0.38 kilograms only. Okay, so over here they say take g is equals to 9.8 meters per second squared. So calculate the initial weight of the rocket. Now for A part 1 is quite simple. The initial weight of the rocket will be 1.3 multiplied by 9.8, which will be 12.8 newtons. Part 2, calculate the final weight of the rocket. The final mass of the rocket is 0.38, and then you multiply by 9.8. That should give you 3.73, I think, plus or minus some decimal places. And then they ask us to calculate the time for the fuel to be burned. Well, the initial mass is 1.3 kilograms and the final mass is 0.38. So the change in mass will be 1.3 minus 0.38. This will be the change in mass. And then the fuel burns at 0.23 kilograms per second. So the final answer should be around 4 seconds. Right, so the fuel takes 4 seconds to burn. Now on the graph above, draw a line to represent the variation with time of the weight of the rocket during the first 5 seconds. Now let's take a look at the starting weight. So initially the starting weight should be 12.7 newtons. So let's put down 12.7 newtons, 10, 11, 12.7 newtons should be somewhere around here. The final weight after 4 seconds should be 3.72 newtons. So let's take a look at 4 seconds, and then 3.7 newtons should be around here. Now, after the rocket has used up all of its fuel, its weight shouldn't go down anymore. So after 5 seconds, the weight of the rocket should still be 3.72 newtons. So this is roughly what the rocket's weight should look like. Okay, so this is the weight of the rocket. So now next, hence state the time delay between firing the rocket and liftoff. Let's take a look at the rocket on the launch pad. This is the rocket sitting on the launch pad, okay? Now the weight of the rocket is 12.7 newtons, and the force on the rocket initially is 0. So the force initially is 0. So it's not going to lift off. No lift off. Right. So after some time, the weight on the force on the rocket is now 10 newtons. 10 newtons is still no lift off. No lift off. So when will the rocket lift off? The rocket will lift off when the force on the rocket increases to 12.7 newtons. That's when it's going to start floating off the ground. So the point at which the rocket lifts off the platform is actually over here around, let's say, 5.5 or 5 seconds, right? So the time delay will be 0.52 seconds, for instance, all right, or 0.53 seconds. So write down an equation to represent the relation between the resultant force on the body, the time over which the force acts, and the change in momentum of the body. Well, this is just the impulse equation. So F delta T is equals to delta P. So on the graph above, shape the area which represents the change in momentum during the first 3 seconds after the rocket is fired. Now, one thing that we need to understand about this equation is that F is the net force. So the equation is actually F net delta T is equals to delta P, because only a net force can change the momentum of an object. Right, so only a net external force can change the momentum of an object. So what do you mean by net external force? Okay, so here are the forces acting on the rocket, right? So when the rocket has lifted off the platform, so there will be a thrust on the rocket, T, and then there will be a weight of the rocket, mg. So the net force on the rocket will be calculated as T minus mg. Where do we find this on the graph? On the graph, this thrust line is T and this weight line is mg. So the only time when the rocket is actually going to lift off is when T is greater than mg, and they want us to do this, okay, over 3 seconds. So this is the area for which the rocket will have a change in momentum. So this will be the delta P from T less than 3 seconds. Okay, so this is the change in momentum of the rocket within the 3 seconds after the rocket is fired. Now, of course, the rocket engine only turns off at 4 seconds, but we don't know what is the thrust of the rocket after 3 seconds is not given to us. Okay, so the answer for C part 2 is this shaded area over here. Right. Now we're going to go on to a new topic for question 14. Let's take a look at question 14. Now question 14 makes use of two principles. The first principle is the principle of conservation of momentum. Now it's important to remember what the principle of conservation of momentum is. So make sure you memorize this. The principle of conservation of momentum states that in an isolated system is one where there's no energy or mass entering or leaving the system. In an isolated system, the total momentum is conserved provided no resultant external force acts on the system. Now, conservation of momentum is also usually paired with two types of collisions. The first type of collision is called an elastic collision. Now, in elastic collisions, the total KE of the system, all objects inside, before the collision is the same as the total KE after the collision, meaning that no energy is lost or converted into sound, heat, or light during the collision. Now note that for elastic collisions, the relative speed of approach is equal to the relative speed of separation. Now for inelastic collisions, the total KE of the system before and after the collision is not the same. So for inelastic collisions, we don't know anything about the way that the velocities are distributed. If you don't understand any of these concepts, you must look at your lecture notes or SLS again. Okay, so let's take a look at question 14, and this is how we draw it. Now, these are the steps to solve collision question. So the step 1 would be draw the diagram of before and after collision. All right. So let's read the question. A neutron of mass 1u, so this is a neutron with mass 1u, is traveling with a speed of 6.5 times 10 to the power of 5 meters per second, colliding with a stationary carbon atom of mass 12u. The carbon atom moves off in the same direction as the neutron with a velocity of 1 times 10 to the power of 5 meters per second over here later on. Now the step 2 over here is to draw all the unknown velocities to the right. Now, you notice that I don't know the velocity of the neutron over here, but I've drawn it to the right anyway. Now, this is because when you take unknown velocities to the right, then if you get a negative answer, it means it is to the left. So the next step 3 is to write the momentum equation using COM. Now, the conservation of momentum states that the initial mass m1u1 plus m2u2 will be equals to the final momentum of the system m1v1 plus m2v2. So we can easily fill in all the details. The mass of the neutron is 1u, right? The speed of the neutron is 6.5 times 10 to the power of 5. The mass of the carbon is 12, but the speed is 0, so that's a 0. Now, over here, the mass of the neutron is again 1u. The velocity is unknown, so we put down v. The mass of the carbon is 12u, and the speed is 1 times 10 to the power of 5. So this very easily, we can get the v is equals to negative 5.5 times 10 to the power of 5. Now, so this means that what is the negative sign means? Therefore, the neutron, okay, moves to the left. Okay, So the neutron velocity is 5.5 times 10 to the power of 5 to the left. Okay, to the left. So that means that actually the neutron bounces off. Okay, so state whether the collision is elastic or inelastic. So for inelastic collisions, all right, so we check the RSA, the relative speed of approach. Okay, so the neutron is going this way at 6.5 times 10 to the power of 5, and the carbon atom is 0. So the relative speed of approach is 6.5 times 10 to the power of 5 meters per second. Now what about the relative speed of separation? Now for the relative speed of separation, the neutron is moving to the left at 6.5 times 10 to the power, the neutron is moving to the left at 5.5 times 10 to the power of 5, and the carbon atom is moving at 1 times 10 to the power of 5. So the relative speed of separation will be 5.5 plus 1 multiplied by 10 to the power of 5, which is 6.5 times 10 to the power of 5. Now you notice that the RSA is equals to the RSS. So we write down, since RSA is equals to RSS, the collision is elastic. So this is the way, okay, to determine whether the collision is elastic or not. Now, so next, we're going to go to part B, which is a different question. So here we look at part B, right? A piece of plasticine of a mass 0.2 kg falls to the ground and hits the ground. It does not bounce but stick. By considering only the plasticine, describe the change in momentum. So here is the plasticine, okay? It's going at 8 meters per second, and the mass of the plasticine is 0.2 kg. When it hits the ground, it sticks, so the velocity here is 0. Now, what are the changes in momentum? Sorry, it bounced, the question bounced off. Okay, by considering the plasticine, describe the changes in momentum only. So the plasticine, considering the plasticine, the initial momentum will be equals to 0.2 times 8, okay, which is equals to 1.6 kilograms meters per second. Okay, so the final momentum is equals to 0 kilograms meters per second, which means thus the change in momentum is negative 1.6 kilograms meters per second. Now, what does this mean over here? This means that the plasticine's momentum has changed, okay? So why has it changed? Now, the reason why the plasticine has changed is that, okay, the plasticine experiences a net force from the ground, okay? Thus, its momentum is not conserved, because in order to conserve momentum, you must have to have conservation of momentum. There must be no resultant external forces on the system. So if you consider the plasticine on its own, there is a net force on the plasticine, so the momentum cannot be the same. Okay, so in that case, if you consider the plasticine alone as a system, if the plasticine is the system, then the system's momentum is not conserved. Now, what about if you consider the plasticine and the Earth as a system? So if you consider the plasticine and the whole Earth as the single system, then its momentum is conserved. Okay, so the total momentum of the system consisting of the plasticine and the Earth is conserved, as there is no net external force acting on the system. Because you see, both objects are now in the system. The plasticine will exert a normal force on the ground, and the ground will exert a normal force on the plasticine. But since these two forces come from inside the system, they are considered internal forces. And remember, internal forces will not count in conservation of momentum because momentum can only be changed by external forces. So the momentum of the system can only be changed by external forces. So in this case, if you consider both the Earth and the plasticine as a system, then its total momentum remains unchanged. Now, by considering the type of collision, explain the changes in the kinetic energy of the plasticine. Now, how do you know whether it's a elastic or inelastic collision? All right, so let's take a look. So this is the plasticine, this is the Earth. Okay, I draw the flat Earth because I don't have enough space. Okay, so the RSA is equals to 8 meters per second because the Earth is not relatively moving relative to plasticine. And over here, the RSS is equals to 0. Okay, now since the RSA is not equal to the RSS, the collision is inelastic. Now, and furthermore, not only is the collision inelastic, but the velocity of the plasticine is 0 at the end. So it is called a completely inelastic collision. Completely inelastic. Now, in a completely inelastic collision, there is the maximum loss of the kinetic energy. Okay, maximum loss of the Ke of the system. Okay, so what is the energy converted to? The total kinetic energy is not conserved because the Ke of the plasticine is used to deform the plasticine when it collides with the ground. This takes up most of the energy. Most of the energy is used in deformation. Okay, depending on how badly the plasticine is deformed, most of the energy will be lost in deformation. Now let's take a look at part C. Two spheres of masses m and m are moving directly towards each other with speeds v and v as shown. The product mv is greater than the product mv. Suggest whether both spheres could be at rest during the same time during the collision. Now let's take a look at the center of mass of the system. This is center of mass of the system. Center of mass. Okay, or sometimes we call it the center of gravity of the system. Now, because this mass is so big and is moving to the right, okay, over time, the center of mass of the system will shift to the right. So even as the masses are moving, all right, and then maybe the mass will touch each other, and then after that it will bounce away. But still, the center of mass of the system will still be moving to the right. You see, over here, the center of mass of the system constantly moves to the right over time. Okay, so the question now is, can both spheres have 0 speed at any time, at a single time during the collision? Okay, now the answer is no. The answer is no. You see, if this is an isolated system, since no external resultant force act on this system, you must always write this, okay? Since no external resultant force act on the system, the total momentum is conserved. And since the initial momentum is not 0, right, both objects cannot be at rest at the same time. Since if that happens, the total momentum would be 0. So here is the logic. Here's the logic. Conservation of momentum states that total momentum greater than 0 if the velocity of both objects equals to 0, then the total momentum is equals to 0. But this contradicts. Therefore, v1 and v2 cannot equal 0 at the same time. Simple as that. So that means that if the total momentum is non-zero, then they cannot both be stationary at the same time. One of the balls must always be moving. Okay? And that is question 14. Alright, let's take a look at question 15. Now in this question, the question is about the principle of conservation of momentum. Now, conservation of momentum states that in an isolated system, the total momentum is conserved provided no resultant external force acts on the system. That's a very important law that up to today has not been violated, even with Einstein and everything. So please remember it. Okay. Now, for elastic collisions, the total KE of the system before and after the collision is conserved. And the shortcut to know whether it's elastic or not is that for elastic collisions, the relative speed of approach is equal to relative speed of separation. Now, in qualitative terms, what can be stated about the subsequent motion as a result of knowing that the collision is elastic? Well, very simple. If the collision is elastic, the relative speed of approach is equal to the relative speed of separation. Now, what about knowing that the collision is head-on? If the collision is head-on, then the objects will separate in a straight line without any deviation from the original path. So if the collision is head-on, then after they collide, the objects will separate along the same line. Now, if the collision is not head-on, then after the collision, the objects may separate out in different directions. Okay, Ken? However, non-head-on collisions are rarely tested in A-levels. You might need to study them, but the chances of it coming out is relatively low. Now, using your answer to A and B, determine the speed of separation of the two molecules after the collision. Well, this is a relatively simple problem. Okay, first of all, we'll draw the before collision and then we'll draw the after collision. Now, before the collision, the velocity of the left-hand molecule is 1.88 times 10 to the power of 3 meters per second. Okay, the hydrogen molecule, and the oxygen molecule's speed is 405 meters per second. So knowing that the relative speed of approach must be equals to the relative speed of separation for a elastic collision, the relative speed of approach would be 1.88 times 10 to the power of 3 plus 405, and this is equals to the relative speed of separation. So the relative speed of separation will be 2285 meters per second. Okay, now part D, apply the law of conservation to the momentum. Now, so in part D, let's give this M1 and U1. Okay, now the mass of the hydrogen atom is 2U and the speed is 1.8 times 3. And the mass of the oxygen molecule is 32U, and the speed of the oxygen molecule to the left is 405. Now, after collision, we are going to write the unknown velocity to the left, V1, which is 2U. Now, we always draw unknown velocities to the right, so we're going to write 32U, okay, also going to the right, and we put it as V2. Now, the reason we do this is because if the velocities turn out to be negative, then we know it's to the left. Now, using conservation of momentum, where m1u1 plus m2u2 is equals to m1v1 plus m2v2, we remember that all velocities going to the left are negative. So let's write down 2u multiplied by 1880. I don't like to write 10 to the power of negative 3, 10 to the power of 3. Then we write 32u minus 405 is equals to 2u v1 plus 32u v2. Okay, so then we can simplify the equation, okay, on the left to get v1 plus 16v2 is equals to negative 4600. Now this will be our equation number 1. Now next, we need to apply a conservation of kinetic energy for elastic collisions. Alright, knowing that RSS is equals to 2285. Now RSS equals to 2285. Let's consider, alright, what's happening. Here is the hydrogen molecule and here is the oxygen molecule. Both of them are assumed to be moving to the right. If they are separating, this must be faster and this must be slower. So what does this mean? It means that the difference between their speeds, v2 minus v1, is equals to 2285. And this is equation number 2. Okay, so now you don't have to show the working, but what you need to do is to write solving 1 and 2, and then you can just write v1 equals to and v2 equals to. Okay, so v1 equals to minus 2420 meters per second and v2 equals to minus 136 meters per second. So what does this mean? This means that actually, since both velocities are negative, they are actually moving to the left. So let's see what happens, okay, in the actual collision. So over here, this guy is moving at 1880 and this guy is moving at 405. They collide, and then this guy is moving backwards now at a greater speed, 2470, and this guy is moving in the original direction at a slower speed, 136. Now this kind of makes sense because if you think about playing tennis or something, you know, when a tennis ball comes towards you and you swing the racket, pum, the tennis ball flies away with an even greater speed. So what we're seeing here is that the hydrogen atom is a tennis ball and the oxygen atom or molecule is the racket. And it's smacking the hydrogen and it's flying away with greater speed. Okay, so this is how you do collision questions. They're always very standard. They're always done the same way. Okay, so I hope you will learn this method. Okay, that's the end of question 50.